Okay, now it's time. The session is start. The first speaker is Nathan Claude, and Nathan Claude, and the title is Local Equivalence of Stabilizer States. Sorry, please start.
Okay, thank you for the introduction. Hello everyone, good afternoon. So my name is Nathan Claudet, and this is a joint work with Simon Perdrix. So I will begin by giving a recall on some notions like graph states, related problems like local unitary equivalence and local Clifford equivalence, and we will see how it relates to a graphical notion called local complementation. Okay, so graph states are quantum states which are in one-to-one correspondence with mathematical graphs. So the vertices represent the qubits, and the edges represent the entanglements. And so to prepare a graph state, for each vertex you prepare a qubit in the state plus, and for each edge you will apply some control Z gates on the corresponding qubits. So you'll end up with graph states which can be represented by a graph. Okay, so graph states are a subfamily of the well-known stabilizer states because they have some stabilizers which are related to the structure of the graph. And I want to stress that everything that I will be saying in this talk will be also applicable to stabilizer states because graph state and stabilizer state are somewhat similar in terms of local operations. So you can replace everything I say about graph states by stabilizer states. Okay, so graph states are very useful as entanglement resources in many protocols ranging from measurement-based quantum computation to error correction. And so it is a fundamental problem to know whether two graph states have the same entanglements. And so the more general way to formalize for graph state having the same entanglements is to speak of SLOCC equivalence, so whether two graphs can be related by operations in the SLOCC fragment. So SLOCC meaning stochastic local operation and classical communication. So actually the problem is a bit simpler because it was shown like in 2004 that if that two graph states are SLOCC equivalent if and only if they are local unitary equivalents, meaning that they are related by a tensor product of single qubit unitaries. So in this case, we can wonder if these two graph states have the same entanglements, so whether or not they can be related by local unitaries. And in this case, this is the case. We can show some local unitaries that maps one graph to the other. But it's not clear how do we know that the two graphs have the same entanglement only from the graph structure. So it's not trivial to see that we have some sort of graphical representation. The problem of graphically representing entanglement becomes much simpler when restricting local unitaries to the Clifford group. And so we say that two graph states are local Clifford equivalents if they can be related to each other by local unitaries in the Clifford group. So this is more constraints than the original problem with local unitary equivalence. So those two graphs are related by Clifford local operations. And I said that this is an easier problem because we know by a result from Van der Nest, Dain, and Demour in 2004 that two graph states are local Clifford equivalents if and only if the two corresponding graphs are related by a graphical operation that we call local complementation. So local complementation actually was introduced in the 60s by Kotzig in a context which is not quantum information. And it's pretty simple. So local complementation on some vertex U consists in complementing the open neighborhood of U. So to see an example, here if I want to apply local complementation on 2, I will check the neighborhood of 2, which is 1, 3, and 4, and I will complement the subgraph, which is induced by 1, 3, and 4. So it will be like toggling some edges. Okay, so this is for local complementation. And like I said, this completely captures the local Clifford equivalence of graph states, which is nice. So it's even nicer because we know, thanks to Boucher in the 90s, that there exists an efficient algorithm to know whether two graphs are related by a sequence of local complementation. And as you may guess, this directly implies a polynomial time algorithm to decide if two graph states are related by local Clifford operators. Okay, so we see that for local Clifford, this is nice. We have local complementation. And this is not maybe as trivial for local unitary equivalence. And for some time, there was this conjecture, which was that local unitary equivalence and local Clifford equivalence coincide for graph states, which would have been great news. But unfortunately, this is not the case. Like local unitary equivalence and local Clifford equivalence does not coincide for graph states. So more precisely, in 2008, G and others presented some pairs of graph states which were local unitary equivalents, but which were not local Clifford equivalents. So namely, when you see this graph, if you want to toggle the edge in red, you can do it using some Clifford operation along with some T-gates, so which are outside of Clifford, but you can show that you cannot do it using only a local Clifford operation. So this is a counterexample, sort of say, to LU equal LC. And as a consequence, local complementation does capture local Clifford equivalence, but it does not capture local unitary equivalence. So yeah. So like in the last 20 years, so there have been some efforts to characterize some families of graph states for which local equivalence, local unitary equivalence, and local Clifford equivalence do coincide. So this is the case, for example, for graph states on at most 8 qubits. This is the case for complete graphs, which corresponds to GIJ states or CAD states. This is the case for complete bipartite graphs, and for some reason it is the case for graphs with no cycle of length 3 or 4. But we see that this is a bit constrained, like this is for very specific families of graphs. And in general, we would like to say something about our original problem for any graph. So the question is, can we construct some graphical characterization of local unitary equivalence for any graph? And this is what we did in this work. So the idea is to generalize the notion of local complementation in order to capture the local unitary equivalence of graph states. So I will try to give you a glimpse of the operation, so the generalized local complementation, but I will not enter like technical details. So first, notice that if you apply a sequence of local complementation on the graph, you may leave the graph invariant. So, for example, if we apply one local complementation over the vertex 1, 2, 3, and 1 again, let's say, you end up with the same graph as the one you started with. So, in other words, every edge was toggled an even number of times. But we can say that some edges were toggled a number of times which was a multiple of 4, and some edges were not. And so one way to refine this idempotent, sort of say, local complementation is to define what we call a two-local complementation. And so we will toggling every edge that was toggled 2 modulo 4 times by the idempotent local complementation and leave invariant the other edges. And so in this example, if we apply a two local complementation on the multiset 1, 1, 2, and 3, we end up with this graph. And so we have also some additional conditions that I won't get into in order for the two local complementation to be valid. So as you may guess, we can generalize it to arbitrarily higher integer. So we can define three local complementation as a refinement of idempotent two local complementation, and so on, until we have an infinite family of graphical operations that are parameterized by an integer r. And so we have those R local complementation. So yeah, so this is for the local complementation. And with this, we can enter our main results of the paper. So first, we can see that this is a valid generalization of local complementation because two graphs are related by R local complementation if and only if the two corresponding graph states are related by local unitary in the level R+1 of the Clifford hierarchy. So this is indeed a generalization of what we didn't know about local complementation, in the sense that local complementation corresponds to local Clifford operation, because in the case R equal 1, the R local complementation are actually just the local complementations, and the level 2 of the Clifford hierarchy is actually the Clifford. Okay, so this is nice, but I recall that our main focus is on local unitary equivalence, and in fact, we have the property that two graph states are local unitary equivalent if and only if the two corresponding graphs are related by R local complementation for some R. So this is nice because, as we wanted, we have a graphical characterization of local unitary equivalence. So we have a way of knowing if the two graphs have the same entanglement by just looking at the structure of the graphs. And we also have some nice consequences quantum-wise, because this implies that if two graph states are local unitary equivalents, then the local unitaries can be chosen to be in the Clifford hierarchy, which is a strong result by itself. Okay, so to see some sort of visualization of this, we know that if two graphs are related by local complementation, then they are related by two local complementation, and then three local complementation, and so on. And to the infinity, we will have every sort of local unitary equivalence between graph states. And I don't know if you recall the counterexample with 27 vertices, but it's here. Because indeed, those two graph states, so the one with the red edge and without, can be related by Clifford operation and T-gates. And this corresponds to two local complementation. But at this point, maybe you can wonder, is two local complementation enough to characterize local unitary equivalence? Maybe we don't need 2, 3, 4, and so on local complementation. But we show that this is not the case because every R local complementation is necessary to characterize local unitary equivalence. So the idea is to prove that for any R, there exist some pairs of graphs which are related by R+1 local complementation, but they are not related by R local complementation. So at the end of the day, we have an infinite strict hierarchy of local equivalences between graph states. And yeah, this is a nice way of constructing the gap that we had between local Clifford equivalence and local unitary equivalence between graph states. So now let me give you a quick overview of the proof for the main result. So for the fact that local unitary equivalence is captured by R local complementation. So our main tools are called minimal local sets. There are some peculiar sets of vertices over a graph. And so they are invariant by local unitary equivalence. And most importantly, they give us some information on the kind of local equivalences of local unitaries that maps one graph to the other, because they correspond to some stabilizers of the graph states which are of minimal support. So one thing we proved with Simon Perdrix last year is that each vertex of the graph is covered by at least one minimal local set, and this is crucial to the proof because then we can have constraints on the local unitaries on each qubit of the graph states. And we also proved that such a cover by minimal local set could be obtained in a polynomial time. So next, like we have those minimal local sets, and then the idea is to take two graph states that we suppose to be local unitary equivalents. We construct a cover by minimal local set to have some constraints on the local unitaries. Then the idea is to perform some local complementation on the two graphs. in order to put them in some sort of standard form. And in this standard form, the minimal local sets give some nice constraints on the local unitaries. Namely, in this form, the two graphs are related only by x rotation, z rotation, and the identity. And when working a bit on the angles, it can be shown that actually this is exactly the implementation of R local complementation. So at the end of the day, we start from one graph, we apply some local complementation, then one single R local complementation, then some other local complementation. And knowing the fact that local complementation are just a special case of R local complementation, this is just actually a sequence of R local complementations which terminate the proofs. So now before ending, let me give you some nice application of these techniques and of the generalized local complementation. So as I mentioned earlier, it is of interest to know which classes of graph states satisfy that local unitary equivalence is the same as local Clifford equivalence. And it was conjectured in some paper of 2018 that it was the case for some repeater graph states of this form. And we are able to show using the generalized local complementation that this is indeed the case. Like for those graphs and graphs that share similar properties, local Clifford equivalence and local unitary equivalence do coincide. So this is nice. And for the two other applications, they are actually parts of very recent work we did again with Simon Perdrix, again on the application of generalized local complementation. So first, let me recall that previously it was known that for graph states up to 8 qubits, local unitary equivalence and local Clifford equivalence do coincide. So local complementation does capture local unitary equivalence, but there exists a counterexample to LU equal LC, which has 27 qubits. So there is some gap between the two bounds. And we are able to reduce this gap by showing that local unitary equivalence and local Clifford equivalence do coincide for graph states up to 19 qubits. So the idea is that for regular graphs, the combinatorial explosion is huge, so it's hard to generate every pair of graph and to check if LU does equal to LC. But using our techniques, we're able to reduce this problem to some sort of generation of every two local complementation possible, and so the problem becomes much easier to deal with. Okay, and finally, about the algorithmic aspects of local unitary equivalence. It was known since recently that there exists some deterministic algorithm to decide local unitary equivalence of graph states. But using some more work on the generalized local complementation, we were able to improve this complexity to quasi-polynomial complexity. So we have a quasi-polynomial time algorithm to decide local unitary equivalence of graph states. So quasi-polynomial is the number of qubits. Okay, so to summarize, we have introduced a graphical operation, which is a generalization of the usual local complementation, which does capture exactly the local unitary equivalence of graph states. So there are still some important open questions. Namely, it would be nice to know if there exists a counterexample to LU equal LC between 20 and 26 qubits, because the gap is not empty yet. And furthermore, it is still an open question to know whether or not there exists an efficient algorithm, so a polynomial time algorithm, to decide local unitary equivalence of graph states. Okay, thank you.
Thank you for the nice talk. And is there a comment? Yeah.
Thank you for literally a beautiful talk. So I have a question about the characterization that you did up to 19 qubits. Did you take into account permutations, or like how do you deal with whenever there are too many graphs up to permutations? So did you do it for labeled or unlabeled graphs?
So I did it for labeled graph, so the qubits are labeled. But the idea is much simpler than just generating every graphs. The idea is just to prove that at some point, every two local complementation you can think of can be implemented by regular local complementation. So this is much simpler than just generating every graph. So this is how we did it.
Thank you.
Hello, thank you again for a very beautiful talk. So there are certain types of graphs that that are LC invariant. So for example, circle graphs will still be circle graphs after any sequence of local complementations. Does this idea generalize to these R local complementations as well?
I don't know any classes of graph which are invariant by local interior equivalence like this, because it does have a less nice structure than regular local complementation. But maybe there is some work to be done in this area. Thanks.
Thank you. Thank you very much.
Other questions?
Thank you for the nice talk. I was wondering if you could share with us a few more details about the X and Z rotations you had on slide 17.
Okay.
Yes,
what kind of detail do you want?
Well, you said that it implements an R local complementation, but I mean, what do you mean by an X rotation on a graph, for example? Or is the bottom structure not a graph? It's been turned into something else.
Okay, so on the left side and right side, this is a graph. And so by X rotation, I mean that the poly X gate is just the X rotation of angle pi. And so you can do it with finer angles like p over 2, p over 4, p over 8, and so on. So this is the kind of operation that you have. And maybe the thing that's missing, but it's in the paper, is that you can implement R local complementation using those X rotation and Z rotation because they behave somewhat nicely on graphs.
I see. So does that mean that the two pictures at the bottom, the ones that say Vx, Vz, and perp, they contain local operations on their vertices? Or are they just pure graphs, and they're just graph states in another form?
No. The two are graphs. Like, the idea is to stay in the field of graph states through the whole computation. Like, I have not presented the additional conditions or on R local complementation, but in some sense they are here in order to stay in the domain of graph states, because else maybe we would get out and get in the weighted hypergraph state, for example. But the idea here is to stay in graph states.
All right. Thanks a lot for this wonderful talk. So I'm wondering, do you know how to minimize the number of edges, the total number of edges in your graph with your techniques under local uniter?
No, we didn't look into that. I don't believe this will be a very useful application of R local complementation. I believe that local complementation for those kind of tasks may be enough. Like, it's a bit more cumbersome to find R local complementation to apply. So I do think the problem of reducing the number of edges in a graph with local complementation is still to be worked in the case of local Clifford.
Yeah, all right, it's fair.
Final short question. Okay.
So many questions. I mean, is there any relation between the level of the hierarchy that you need and, say, the transversal gates codes that contain this cluster state have, or say the depth of the Clifford circuit you need to map between the two cluster states if you allow non-local? Are there any connections to these other things?
Okay, so I'm not sure about how to answer your question. Maybe just something I can say about this story of Clifford hierarchy is that on the theorem, I say that we are in the Clifford hierarchy, but actually we do have a bit more information on the kind of unitaries that maps one graph to the other. And they are generated by Hadamard gates, by the Clifford gates, and like z gates of angle p over 2 to the r. So I don't know if it helps, but we have a more structure than just saying the level r+1 of the Clifford hierarchy.
Now time is up, so thanks speakers again.